Hi everybody, today we will continue physics revision series, today episode 2. Today we will continue to discover how can we deal, for all our students, how can we deal with the different types of questions preparing to the final exam of third secondary. Today we'll introduce the concepts and the problems of chapter 2. Of course, we know that the title of chapter 2 is the magnetic effect of the electric current. At first, we'll start with chapter 2 summary. Of course, the first concept of chapter 2 is what's meant by magnetic flux. Of course, you know that magnetic flux is the number of flux lines passes normally through an area. Here, we haven't a certain area. We are talking about any area. So, when we are talking about the number of magnetic flux lines passes normally through an area, it is magnetic flux. But when we modify this concept to be, it is the number of magnetic flux lines passes normally through a unit area. Unit area means area of 1 meter squared, okay? Then we deal with magnetic flux density. So, what is the difference between magnetic flux and magnetic flux density? Is magnetic flux density, we are dealing with a certain area or unit area. Okay, the symbol of magnetic flux density is beta. Beta equals phi divide area. So from here, we can conclude the units. Beta is measured by Tesla. Tesla from the rule equals phi is measured by Webb, area is measured by meter squared. So here we can conclude that Tesla equals Webb per meter squared. Okay, here, what are the most famous questions about this part? Here, of course, the first question in our exam is what's meant by. Number A, what's meant by the magnetic flux density at a point is 0.5 Tesla. As we said in our previous lecture, our previous episode, okay, that when we are dealing with what's meant by like this, just replace the concept. Here, the concept is magnetic flux density. We should just replace the concept with its definition. So here, the answer for number A will be the number of magnetic flux lines passes normally through a unit area around this point is 0.5 Tesla. Again, what's meant by the magnetic flux density at a point is 0.5 Tesla. Here, we should replace the concept by its definition. So, here the best answer for this question is the number of magnetic flux lines passes normally through a unit area around this point is 0.5 Tesla. Okay, another question, number B. What's meant by the magnetic flux at a point is 0.3 Weber. Of course, we should differentiate between A and B. In number A, the question asks us about the magnetic flux density. But in number B, the question is the magnetic flux, just the magnetic flux. So here, the best answer is the number of magnetic flux lines passes normally through an area is 0.3 Weber. Then, the second part or the second item for chapter 2 is what are the shapes of the magnetic lines or magnetic field lines around At first, straight wire, then around a circular loop or coil, third around a solenoid. But here we are dealing with a straight wire carrying a current, a circular loop carrying a current, and a solenoid carrying a current. When we make an experiment to distinguish or to just recognize or know what are the shapes of magnetic field lines around a straight wire carrying a current, we will get this shape in the first column. Okay, here as we see, the magnetic flux lines around a straight wire carrying a current, okay, are just concentric circles close to each other with high density near to the wire. The number of lines or the lines are crowded near to the wire, and the distance between them increases as moving away from the wire. So here, okay, what are the shapes of magnetic flux lines around a wire carrying a current? We can say that they are concentric circles close to each other, nearer or near to the wire, and the distance between them increases as moving away from the wire. Explain. Why? Why the number of magnetic flux lines or the magnetic flux lines are crowded near to the wire, but the distance increases as moving away from the wire. Here, of course, we have another question about this. We have a famous give reason about this point. Okay? The most famous give reason about this point is called or states that, give reason, it is most important to build our homes away from the electric wires carrying high currents or high voltage currents. Again, give reason or explain, it is most important to build our homes or our houses away from high voltage wires. Okay? Of course, our best answer is because the magnetic flux lines are crowded near to the wires carrying a current, and the distance between them increases as moving away from them. So it is very important to build our homes away from wires carrying currents. The second column, we are talking about the magnetic field lines or the magnetic flux lines that are generated around a circular loop carrying a current. We can see here that the lines lose its circularity at the center of the loop. At the center of the loop, okay, the shape of magnetic flux lines changed from circle just to be straight line. Why? Why here? Okay, number 3, the magnetic flux density differs from point to another. So here, of course, because at the midpoint, the magnetic flux lines around each branch of the circular loop cancel each other. So here, what are the differences? Or what are the differences between the magnetic field shapes around a straight wire carrying a current and a circular loop carrying current? Around a straight wire, the magnetic flux lines are concentric circles, crowded near to the wire, and the distance between them increases as moving away from the wire. But around a circular loop, okay, there or the magnetic flux lines lose their circularity. Where the magnetic flux lines lose their circularity? At the center of the loop. Number 3, what are the magnetic field lines around a solenoid carrying currents? As we see here, okay, from the shape in column 3, each line here represents a closed path. So in the upper part, we can see that the magnetic flux lines move clockwise, but in the lower part, the magnetic flux lines move anti-clockwise. Then what are the polarity? Okay, and how can we determine the polarity of a solenoid or a loop carrying a current? What are the polarity? Okay, what's meant by polarity? Polarity means that the circular loop, when it carries a current, it is changed into a magnet. Okay, or definitely the circular loop, okay, or the magnetic field around the circular loop looks like that of a short magnet. So here it has magnetic dipole. It means that it has north and south. So as we see here, the side in which the current moves clockwise represents the south, while the side in which the current moves anti-clockwise represents the north pole. This rule is called clock rule. Of course, here, to just be simple for our students, we can depend on this diagram. Okay, when the current moves like this, okay, here the current moves clockwise, okay, or like this. When the current moves or is moved like this means clockwise. When the current moves clockwise, it generates or it represents south pole of the magnet. But when the current moves like this, or like this, moves here anti-clockwise, like this. Okay? Anti-clockwise or counterclockwise. It represents a north pole of the magnet. Okay? And of course, it is very easy rule to determine the polarity of the current. So again, when the current moves clockwise, it represents or generates south pole of a magnet. When the current is moved or moves anti-clockwise, it produces or generates or represents the north pole of the magnet. Then here, when we are talking about the circular loop, we can see here, okay, from the shape, that the upper part, we can see that the current starts to move here for the upper part. It will move anti-clockwise here, like this, okay? So it represents north. But when we are talking about the upper part, this part, we can see that the arrow representing, okay, the movement in the clockwise direction. So it represents the south pole of the magnet. So here, when the circular loop carries current, the magnetic field around the circular loop looks like that of a short magnet. But what about the solenoid? Okay, we can see here from the drawing that the side from which the current emerges, like this, here, the current emerges. Okay, the side from which the current emerges, it represents north. And the other side, okay, from which the current gets in, it represents the south pole. Here, we can determine the polarity for the circular loop and the solenoid. Our next or the third item is, what about the determination of the polarity? It is a most famous question in our exams in Egypt. Okay? you will face this problem or this question exactly in your exam. What is the item? What is the item of the question? Okay, sure, you will face an item which is called mention the use for each of the following. Mention the use for each of the following. Number one, what is the use of Ampere's right rule or Ampere's right hand rule? Okay, so here, Ampere's right hand rule, it is used to determine the polarity of the magnetic flux around a wire carrying a current. Again, mention the use of Ampere's right hand rule. Okay, the best answer is to determine the polarity of the magnetic flux around a wire carrying a current. Next, what about the circular loop, okay, polarity? Here, we use another way or another rule to determine the polarity of a circular loop. Here, as we see in the pattern, or as we see in the drawing, we have here a screw rule, okay? The direction of fastening, okay, in Arabic means اتجاه الربط, okay? Direction of fastening in the upper part here, it represents the magnetic field direction. And the direction of motion, okay, it represents direction of current. In Arabic, okay, when we are tying, when we are fasten, okay, لما بنربط, okay, a screw, مسمار ألوز, direction of fastening, اتجاه الربط, okay, it represents the magnetic flux direction. okay, لما بنيجي نربط مسمار الألوز كده, اتجاه اندفاعه, direction of motion, سواء اتجاه اندفاعه forward or backward, اتجاه الاندفاع ده it represents the current. okay, of course for physicists, لجماعة الفيزيائيين, Ampere's right hand rule and right hand screw rule are the same. okay, because here by using Ampere's right hand rule like this, okay, when it is a wire carrying a current, when we catch or hold the wire like this, okay, the wrist of fingers represent direction of flux and the thumb indicates direction of current. okay, this is Ampere's right hand rule. Of course, it is the same mechanism of right hand screw rule. For right hand screw rule, okay, direction of fastening, okay, اتجاه الربط, represents direction of magnetic flux and direction of motion, okay, represent direction of current. So there is a similarity between right hand screw rule, which is used to determine the polarity of a circular loop, and Ampere's right hand rule, which is used to determine the polarity of a straight wire carrying a current. But what about the polarity of a solenoid carrying a current? Of course, from the figure, you can see that we haven't new rules here, okay? For solenoid, we can determine its polarity by right screw rule like the circular loop, and the Ampere's right hand rule like the straight wire. So here, what are the most famous questions about this item? Okay, the question again, mention the best use or mention the use of number A, Ampere's right hand rule. Okay, of course I can hear from here the answer of my students. Ampere's right hand rule, it is used to determine the polarity of magnetic flux around a wire carrying a current. Number B, mention the use of right hand screw rule. Here we can say It is used to determine the of a magnetic flux around circular loop carrying a current or a solenoid. Okay, the next part is laws and factors. What about laws and factors here? Of course, as we said in our previous episode, in physics it is very easy to deal with factors because most of factors, okay, of physics, it can be concluded, okay, from the rule like this. For magnetic flux density around a straight wire carrying a current, beta equal mu I over 2 by d. Mu, it is the magnetic permeability, and here in Egypt in our curriculum we're just dealing with the magnetic permeability of air and sometimes with the magnetic permeability of iron. We just deal with the two substances. Okay, the magnetic permeability here for air is 4 pi multiplied 10 power negative 7 Web per meter squared. Of course, you know that I is the current intensity. Okay, D, it is the distance away from the wire which carries a current. Here, from the rule, okay, beta equals mu I over 2 by d. What are the factors on which the magnetic flux density around a straight wire carrying a current depends? Of course, the current intensity, beta, is directly proportional with the current intensity. Number two, beta is inversely proportional to the distance from the wire. So, for many times we can say the same words, we can conclude the factors from the rule. What about the factors and the law of the magnetic flux density around a circular coil carrying a current? Okay, the law states that beta, okay, equals mu n I over 2r, where n over, okay, or how can we determine n? Okay, n here means the number of, I can hear, n here means the number of turns. Okay, n here, it can be determined from L over 2 by r. Okay, and we can write it briefly like this. Okay, our main rule is beta equals mu n I over 2r. Mu means, I can hear permeability, n number of turns, I current intensity. What about r? R, it is the radius of the circular coil. This is the radius. So if we have a straight wire like this, okay, it carries a current and it has a length L. When this wire is converted into a coil like this, of course, it carries the same current of the straight wire, and the current will move like this. Okay, what about L here? The length of the wire is changed to be a circle, like this. So here, we can determine from this L equals, L here is changed into just one circle, so it has just one circumference. So L here equals 2 by r. Okay, but when this wire is changed into, okay, circular loop of many turns, so here L is changed into n over 2 by r. So from here, we can calculate n. n equals L over 2 by R. So here, we can calculate or find the n, okay, from this rule. Of course, we can't forget the unit. Beta is measured in Tesla, or as we said, Weber per meter squared. This unit or this unit. Okay. What about the factors on which the magnetic flux density around a circular coil or a circular loop depends? Of course, beta here is directly proportional with the current intensity, here from the rule. Yeah. Then, beta also is directly proportional with n. n is the number of coils turns. Of course, beta is directly with n and directly with I. But here, beta is inversely proportional to what? To the radius of the coil. The third part is magnetic flux density around a solenoid carries current or carrying current. Beta equals mu n small I. This is the main rule of magnetic flux density around a solenoid. Mu is the permeability. N here, okay, we can determine or calculate n. As we see, we replace n with n capital over L. Okay, so here n is substituted by n capital over L. Okay, as we can write here. The main rule is beta equals mu, okay, n I. We can substitute n in small by beta equals mu n over L I. So here n equals what? Equals n capital over L. So n small equals n capital over L. So here n is called the number of turns per unit length. N is the number of turns per unit length. And its unit is, of course, n, it is a number, it has no unit. L, it is measured by meter. Okay? When we transfer meter from here to above, from denominator to be numerator, okay, it will be meter power negative 1. So, n here, okay, it is the number of coils per unit length. Its measuring unit is meter power negative 1. Okay. From the rule, okay, here, or here, we can find the factors on which the magnetic flux density around the solenoid depends. Beta is directly proportional with n small, number of turns per unit length, and also it is directly proportional to the current intensity. Okay. For all our students, the best way to deal with the three different rules is just every time to compare between them. Write them in a comparison. Okay? Why for a comparison? Okay? Because every time, okay, we has a little ambiguous about this point. Ambiguity about this point. So when you write the rules in a comparison, okay, your eyes, okay, and of course your mind can deal every time with the main differences between the three laws and of course the factors of each of them. كل مرة لما تيجي تذاكر الكومباريزون ما بين الثلاثة رولز رص الثلاثة in a comparison. عينك اوكي can we deal usually تمام with the differences اللي بين الرولز خلاص and the same time you can conclude the factors وتقدر تميز ما بين الفاكتورز اللي البيتا بتعتمد عليها in a straight wire in a circular coil or in a loop. دايما تذاكرها على هيئة كومباريزون بين الثلاثة. Okay. What about the problems? Okay. How can we deal with the problems of beta? Here, at first we deal with the problems for beta around a straight wire. Here, as I said for you, I put the laws and the differences as a comparison between them. Okay, in the first column, two parallel wires carrying a current, I1 and I2. In the first column, we have here two wires. The first wire carries I1, the second wire carries I2, okay? And of course, the distance between them is D. In the second column, okay, the first wire carries current I1, the second wire carries current I2, but in opposite direction. Okay. What about the magnetic flux density at a point between them? Okay. Of course, when you draw the flux lines around the two wires in the first case, okay, like this. Here we have two wires. The first wire carries current I1. The second wire carries current I2. Okay? The distance between them is D. Okay? Here, how can we determine the direction of magnetic flux around wire I1? Yeah, right. By using Ampere's right-hand rule. Yeah. Direction of flux is like this. Or here it is inside. So here it is outside. So here we have two different ways to direction or to determine the direction of flux. By using, okay, this way is just to apply Ampere's right-hand rule, okay? Or to use, okay, the other way when the flux is moved into the page, okay, or the flux is moved out of the page. Into the page, it is the flux line is represented as cross, okay, out of page, it is represented as dot. Okay, we can apply the same, so this is beta 1. This is the direction of beta 1. Flux density around the first straight wire. What about the second wire? Okay, we can draw it like this. Also, by using Ampere's right-hand rule. The same. Yeah. This is beta 2. Here, okay, we can apply also the same rule when the flux is moved, okay, into the page, it is cross. Out of page is dot. So here, in the middle or in the midpoint between the two wires, we can see that we have two flux, okay, two fluxes, beta 1 and beta 2. They are moved in opposite directions, okay, dot and cross. So here, the rule is, okay, magnetic flux density at a point between them is B total equals beta 1 minus beta 2. Okay? Of course, here when beta 1 is more than beta 2. And of course, the rule can be written beta 2 B total equals beta 2 minus beta 1 when beta 2 is more than beta 1. Okay. Here, in the middle, okay, or at a point between them, y negative, y B total here equals beta 1 minus beta 2. Of course, because here, the direction of flux, okay, between them is in opposite directions. So here, in the mid point between them, B total equals beta 1 minus beta 2. Of course, for the advanced students, we can write the rule, okay, like this. Okay, absolute. B total equals the absolute difference between beta 1 and beta 2. But here, if we choose a point outside the two wires, okay, a point like here, point like this point, okay. For this point, the direction of beta 1, okay, or beta 2 at first is like this. Yeah, move with beta 2. At this point, this is the direction of beta 2, okay. But what about the direction of beta 1? Of course, in some curriculum or in some country, okay, I think for the Indian curriculum, especially for the Indian curriculum, okay, they prefer to use, okay, this rule, just to, okay, withdraw this line like this. Just increase the length of this line in its direction. And here, at the point, okay, which is located outside the two wires, we can see that the direction of beta 1 is the same direction of beta 2. Okay? So here, this rule is just at a point, midpoint between them. But at a point outside the two wires, the rule here, okay, of course you know that beta 1 in the same direction of beta 2. B total equals beta 1 plus beta 2. So here in the midpoint, the direction of the two flux, beta 1 and beta 2, in opposite direction. But at a point outside the two wires, beta 1 is in the same direction of beta 2. Okay? So here, okay, this is a rule, and this is the rule. This is the rule outside, this is the rule inside. Okay. What about the rules when we have two wires like this, okay, but the current is moved in opposite, but the current is moved, okay, in opposite directions. Okay? The first wire carries I1. The second wire carries I2. Okay? And we want a rule to determine the total magnetic flux density at a point between them. This point here is called A. And of course, we have to determine, okay, a rule to just calculate the magnetic flux density at a point outside them. It is called B. Okay? Depending on Ampere's right-hand rule, at first, we have to draw the direction of magnetic flux. Here, like this. This is beta 1. Around this wire, of course, in opposite direction, like this. This is beta 2. We can see that at the midpoint, beta 1 is in the same direction of beta 2. So, at mid point between them, B total equals beta 1 plus beta 2. Okay. But what about this point? What about the total magnetic flux density at point B? Okay, point B outside the two wires. Okay. As we said, just, okay, withdraw this line like this. So this line represents beta 1 and the other line represents beta 2. So at point B, we can see that beta 1 is in opposite direction to beta 2. So here, if we want to calculate the B total at point B, it equals the absolute of beta 1 minus beta 2. Okay. Here, so we covered the first row and the second row. For the third row, how can we determine the neutral point, okay, between two wires? Between the two wires, I1 over X minus D equals I2 over D. And of course, inshallah, we will apply this in a problem. Okay, between the two wires, when the current, okay, when the two currents are in opposite directions in the two wires, I1 over X plus D equals I2 over D, where D is the neutral point and X is the distance between the two wires. Okay? Of course, the force between the two wires here, when the currents are in the same direction, we can see, okay, at the midpoint that beta 1 is in opposite direction to beta 2. So here, when this, okay, the flux is moved, you can see, okay, like this, anti-clockwise, okay, and this is moved clockwise. So beta 1 in opposite direction to beta 2, so at the midpoint we have attraction. Okay? In the midpoint between the two wires, we have attraction. But here, at point A, which is located between the two wires, okay, beta 1 is in the same direction of beta 2. So they are generated the same poles. Okay, so here between them we have repulsion. Okay. The next part, it is a famous problem here. Two parallel wires, the distance between them is 10 centimeter. The current in the first wire is 3 ampere, while in the second is 4 amperes. In the same direction of the first. Calculate. Number A, the magnetic flux density at a point 2 centimeter from the 2 ampere wire. Then the position of the neutral point. Then the magnetic flux density at a point 2 centimeter outside of them at the side of the first wire. Here, for all, okay, of students, okay, we have an American scientist of education or methodology, okay, his name is Marzano. Marzano said that if you succeed to draw your problem, your physics problem, لو نجحت انك ترسم مسألتك الخاصة بالفيزيكس، okay, the problem is 90% solved. لو انت نجحت انك تحول مسألتك في الفيزيكس من مسألة ابستراكت الى مسألة كونكريت، من شيء مجرد لشيء مجسم، ورسمتها صح، 90% من مسألتك اترسم او اتحل. طيب, we try to apply this for our problem. Okay, here, The first thing is to try to draw your problem. We draw just the first wire carries current 3 ampere. The second wire carries current 2 ampere. The distance between them is 10 centimeter, okay? And we want to find the magnetic flux density, okay, at a point away from 3 ampere by 8 centimeter and from 2 ampere by 2 centimeter. At first, we write the rule of the magnetic flux density, okay, around a straight wire, mu I1 over 2 by D1. Of course, here we know that mu equals 4 pi multiplied 10 power negative 7. So 4 pi multiplied 10 power negative 7 over 2 pi, okay, it equals 2 multiplied 10 power negative 7. So every time, okay, I recommended you to just write or to substitute mu over 2 pi by 2 multiplied 10 power negative 7. This is the first part, is just to write the rule. Then, okay, separate your two wires, okay? Deal with only one wire. افصل مسألتك، اتعامل مع كل واير لوحده. Separately, okay? Here, we will deal, okay, with a problem like this. Okay. Okay, or we can write it here. The first wire is, it carries current I1, which equals 4 ampere, okay, and the distance between them and the point is located here, away from 8 by 8 centimeter. So here, beta 1 equals, okay, mu I over 2 by D. I here equals 4. The distance here equals 8 centimeter. Of course, we should convert it into meters, multiply 10 power negative 2. So here we can find beta 1. Okay, of course it is less. This is for beta 1. Okay. For the second wire, I2, it carries current of 2 ampere and the point is located away from it by 2 centimeter. So here, this D1 and this D2. So here, beta 2 equals mu I over 2 by D. I here equals 2 ampere. The distance here is 2 centimeters, so 2 multiplied 10 power negative 2. So here, we can find beta 1, then we can find beta 2. This is the first or the main point of solving our problem. Then the next step, okay, is at the midpoint between I1 and I2, okay, this is a point here. We can draw the flux as we know, like this. This is the direction of beta 1. And for I2, this is the direction of beta 2. We can see that they are in opposite directions. So here, just to write B total equals absolute of beta 1 minus beta 2. And we can find the answer of number A. And inshallah, in the next episode, we will continue with this part and we will deal with different types of problems. Okay? أرجو النهارده نكون استفدنا وعرفنا, okay, how can we deal with the 3 different types of conductors of or carrying a current. At first, okay, a straight wire carrying a current, then circular coil carrying a current and the solenoid. Okay, لازم لما اجي اعمل ستادينج ليهم او اذاكرهم او اناقشهم لازم اذاكرهم على هيئه كومباريزون. ارجو التوفيق. امتحان الفيزيكس امتحان سهل, ولكن نعرف بس how can we deal with our exam and how can we deal with each item. والسلام عليكم ورحمة الله، ونلتقي في النكست ابيسود إن شاء الله. شكرا.